distinct parts of the lab. So the first thing that you've got to do is figuring out the spring constant. So if you look on the front, is that you've got this diagram and it actually has like this spring support with the hook. Okay, don't use that because my hooks don't line up with my rings and they won't work. So let me just modify one thing. You want to have up here at the top, you want to have like a ring, and then you have like a piece of metal rod, and then the springs can be hooked through with that. So that's the first thing that we need to modify just a little bit. So what we're going to do, the first thing we have to do is collect the data to calculate the spring constant. So here's the deal. So for example, I've given you like all the different masses that you've got to use, like for example 0.5. So you're going to take a 0.5 kilogram mass and you're going to suspend it. So one of the things that you need to establish first is the location of this second ring down. So you want to set this so that the bottom of that ring is exactly in line with the bottom of the hook of the spring, because that's what we're going to use as our equilibrium position. So sit here and just eyeball it, like I just this little bit. Okay? Got some action like that. So this point here is going to be this equilibrium point. So everything is going to be measured from the bottom of this ring. So it's important that you get that bottom of that ring right. So you're going to go through, and this is going to be, at the beginning is going to be the same as what's going to happen with the very first lab that you did. You're going to take a half a kilogram mass. Now, so help me, if you ask me, Mr. Burkamp, how do we calculate the weight of a half kilogram mass? I'm just going to have a heart attack. Okay? So let's not do that. So, yeah, even if you don't know, just don't ask me. Find a friend, just don't ask me. I hate to say that as a teacher, but it's true. So you can take a half kilogram mass, you're going to suspend that, you're going to measure how far this thing stretches. So you're just going to measure from the bottom of the spring down to here. Okay, boom, there you go, not a big deal. And you're going to get all of these points. Okay, so you're going to have all these points on this graph. So because we're dealing with energy, which graph are you going to put, or which value are you going to put on the y-axis, and what are you going to put on the x-axis?
Force.
Force here, elongation here. Meters, newtons. Now, some of you don't understand this concept of a best fit line and why you draw it. So, you know you're going to start at 0, 0, because if you don't have any elongation, you know there's no force, because you know 0, 0 is one solid point. So you're going to go in here and you're going to have these points, and they should be pretty linear. Okay? If you're getting a quadratic function, you have done something horribly wrong. Now, here's what's important to remember. You're plotting elongation, not length. Okay? I don't want the length of the spring. I want to know how far it's moved from that equilibrium point. So then you're going to come in here and you're going to draw a line of best fit. Okay, it's going to split these points. Something like this. Okay? Now, once you get this done, and it's going to be done on graph paper, don't ask me, do you have to draw it on graph paper? Yes, you have to draw it on graph paper. That's why it's called a graph. So, you're going to set up your scale, you're going to come out here. Now, read the instructions. So on section 2, I tell you, whatever points you're going to use to find the slope of that line, I want you to circle those points, whatever points that you choose, and write the coordinates on this. Because everybody's data is going to be different. So I just want to clearly see what points did you pick to find the slope of the line. Now, here's the deal. The points that you pick have to be on the line. Okay? That's the whole point of a line of best fit. Okay? Now, if your data points happen to go through the line of best fit, fantastic. You can use those. Fantastic. But if none of them do, you can't use them. So I don't care which points you pick, I just want to make sure that this is that I can clearly see what you're doing, because everybody's line is going to be a little bit different. Now, and I tell you, in that space on the front of the lab, you're going to show me how you calculated the slope. This minus this over this minus this, boom, you're off to the races. Make sure that you have the correct units. Now, here's the next thing that you're going to need to do. When you get down to line number 3, there's an asterisk right here in this column where it says the elongation at 1.5 meters, or the 1.5 kilogram mark. So eventually we've got to do a whole bunch of other stuff with this graph involving area. So here's what I want you to do, and I tell you this in the instructions, but I'm going to make sure everybody understands this. So you're going to find that maximum elongation. This is what we're going to use as our reference. So you're going to go out here, wherever that maximum elongation is, and you're going to draw a line with a ruler straight up to where it crosses the line of best fit. Okay? So you're going to find your maximum elongation. You're going to look at your data table and you're going to find that point. And then you're going to transpose the line straight up to where it crosses the line of best fit. Then you're going to come over here and you're going to see what value of force corresponds with that. Then you're going to write that data point here. So when you get done, you should have 3 distinct labeled points on this graph. So this data point here, where it crosses this line of best fit, it might be the force that corresponds with it, with that maximum elongation. Odds are it's not. But here's what is the absolute truth. You're here, you're going to come up, you're going to draw this with a ruler, you're going to circle this point, you're going to figure out how much force corresponds with it based upon the line of best fit. Not your data point, okay? Not the actual data set, but it's going to be the point that corresponds with the line of best fit. You're going to use that a lot on the next page. So that's why you've got to have this. So you're going to get your lines, you're going to get your data, boom, plot them, draw the line of best fit, use a ruler, make it look nice, all that jazz. Everybody cool with that part? Okay. Now, once you get done with that, and you just have to get the data. You don't have to actually have the line of best fit to complete the lab. That's just one of the things that you're going to have to do. Now, here's the next thing that you're going to do. Then we're going to actually make this thing oscillate. So this is where you've got to have the bottom 2 rings. So you can have like a ring here, and like this. So you're going to use 1.2 kilograms, okay? Okay? So this is why this has to be lined up just right, because it has to oscillate in the middle of these rings. Especially the bottom one. Okay. So you're going to get this thing set up, and you're just going to make it oscillate like this. So what you want to do is set the top ring where it's at the top of the oscillation, and you kind of have to eyeball that. And then you're going to have the bottom ring at, oddly enough, the bottom of the oscillation. Okay? So you're going to, now, here's what you don't do. Don't like stretch it down, hold it to that point, and then let it go. It's not going to oscillate in those points. You have to get it oscillating and then set your rings. Okay? That's the trick. So, now, let's talk about energy. So as this thing is oscillating, you have 3 types of energy involved. So what are the 3 types of energy that you've got? Kinetic what? It's moving, right? You have a mass that's moving. So that's going to be 1/2 mv squared. What else do you have? Potential energy in the spring, right? So that's going to be 1/2 kx squared. And you got one other form. Right? And you got a little MGH action. Okay? Are any of those values constant throughout the oscillation? Why is the kinetic energy not constant? Bree, why is the kinetic energy changing? Yeah, okay? It's oscillating back and forth. Does the velocity ever go to zero? No. Even when it's oscillating.
Yeah, because it changes direction.
Yeah. So it goes to zero at the top and bottom because it's got to change direction. So there's going to be points where the kinetic energy is going to go to zero. Okay? Is us always changing?
Yes.
Why?
Because the x is changing, the elongation is changing.
Yeah, if you change x, you change the amount of energy stored in the spring. When is the energy stored in that spring going to be at its maximum? At the top of the oscillation or the bottom of the oscillation?
Bottom.
Bottom. Why?
Because that's when it has the most elongation.
Yeah, that's when you have your greatest elongation. This is when you're going to have your biggest value of x. Now, when's it going to be at a minimum then? Up top. Now, here's what's important. When you look at this oscillation, even though it's oscillating, your us does not go to zero, because even at the top of the oscillation, this thing is still stretched from its equilibrium point. So even though it's at the top of the oscillation, us is not zero. The only way us goes back to zero is if that oscillation took it all the way up here to the top. Okay? Which we're not going to do that because that's going to be, no. That's way too big an oscillation. So your us is never going to go to zero. Now the UG gets a little bit dodgy in terms of how we're going to deal with UG. UG is a relative value based upon where it is at the beginning and then where it is at the top. So your UG calculation is going to be based upon, here's that top ring, here's your equilibrium ring, and here's your fourth ring. So if you look on the front of the lab, you have three different measurements that are involved. You have an X1, which is how far it is stretched at the top of the oscillation. You have an X2, which is how far it's stretched at the bottom of the oscillation. And then you have a height calculation, which is the distance in between the rings. So basically what we're saying is that our change in UG, we're just saying here's our baseline. Okay, this is when it has like no UG. And then we're lifting it to this height, so that's going to be our change in UG. Otherwise, it's going to get weird because then you're basing it from the ground and it's just going to get real complicated. So, because we're talking about a change in energy, we're just looking at this value here, from the bottom of the oscillation up to the top of the oscillation. So, it's important that you look at what you've got. So, you have X1, okay, this is how far it's stretched at the top of the oscillation. X2 is how far it's at the bottom of the oscillation, and H is the difference between those points. It's on the front of the lab, but that's what you got to understand. So you're going to calculate three different values of energy. You're going to calculate us based upon X1. You're going to calculate us based upon X2, and then you're going to calculate the potential energy change that goes from lifting it at the bottom to lifting it to the top of the oscillation. So those are the three calculations that you're going to do. So the first set, get it going, maybe kind of have like a smallish kind of what we call amplitude. Amplitude is how far it moves from an equilibrium point. So you're going to have like a smallish kind of amplitude. Set your points, they're probably going to be fairly close together. So once you kind of get a feel for how the system's going to work, then on your second set of trials, okay, on your second set of trials, you're still going to use the 1.2 kilogram mass, but then you're going to have a bigger oscillation. So then maybe pull it down a little bit farther, okay, get some action like this going. So you're still using the 1.2 kilograms, but now you're going to have a bigger oscillation. On the third set, you're going to take off the 200 grams and you're going to put a half a kilogram mass on there, and then you're going to have 1.5 kilograms in terms of your oscillation. So you're going to have 2 with 1.2, 1 with 1.5. A small amplitude, a large amplitude, and then that last one with 1.5 kilograms. Now, let me clarify this. Where I have us1 equals x1 and us2 and us equals x2, that doesn't mean that they're equal. I'm just telling you to calculate it using x1 and using x2, okay? Your distance can't be joules, all right? And it's like, it's one of those things when you type up a lab, you think, oh, this is what I want them to use. And then kid goes, oh, us is the distance. Like, God, no, okay? So that isn't an equality, all right? Us is not a distance, okay? You're going to use x1 to calculate it, and you're going to use x2 to calculate the second one. They are not equal, okay? Oh, Lord. Now, here's what I want on the calculations of U1, U2, delta us, and up. I don't want to see all of the calculations. I just want to see these calculations for trial 1. Now, what I don't want you to do is write down the formula. There's a difference between writing down the formula and showing the numbers. I want to make sure that you are calculating this correctly. So when I've got U1, I want to see 1/2 kx squared. You're going to have your slope of your line, and then you're going to multiply that by x1 squared. That's why you've got this big line. That's what I want to see. And then you're going to do the same thing for U2. You're going to take 1/2 k, that x distance squared, and then you're going to have the two values, and then you're going to find the change. And then you're going to have up. Now, if you want to do off to the side all those trials, you can. But the ones that I clearly want to see is this, where you've got U1, U2, delta U, and up. Okay? We're good. So, what I would recommend, because it's Wednesday and it's short in class, I would get all of the data and then go back and then start to draw like the graph. When you draw the graph, you have an entire sheet of graph paper. This is going to be based upon very good data and the quality of your graph. Draw your graph big, okay? Pay attention to the units. Don't draw a little postage stamp graph. It just annoys me. Then you got a bunch of questions to answer. So I would get all of your data, including the oscillations. Then I'd go back, and then I'd find the slope of the line, and then I'd start to do all the calculations. Logan,
Do you want one graph per group or one graph per group?
what's your gut feeling?
Per group. Every lab we've done per group.
It means like the sketches.
You've done like a pre-lab sketch as a group, but no, everybody's doing their own graph. Okay. Just for clarification, everybody is doing their own graph. Okay. All right. Any other questions? Once, twice, sold. Now, when y'all get done, because you guys are the last group that's going to do this, take the rings, and you'll see that there's a tub there. Take the rings off, put the rings back in there. Take the ring stands, put those underneath, strip everything down. Make sure that you clamp this down so that it doesn't fall.